Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Our speaker today is Vivek Sheshadri from Carnegie Mellon University, and he works there with Onur Mutlu and Todd Mowry. Vivek's done a lot of work at the intersection of computer architecture and systems, and he's super creative, as will be evidenced by his talk today. And he somehow figured out a way to, consistently publish at the top conferences, architecture conferences. I've crossed paths with Vivek very briefly at CMU. He's a pretty intense squash player. So those of you meeting him later today, if you want him to really think on his feet, take him to Pro Club. Right? So, welcome, Vivek.
Yeah. Thank you, Amar, for the introduction. I like the way he said, found a way to consistently publish at top conferences. I hope it's an intersection of good ideas and also good writing and not some kind of gaming system. Anyway, so in this talk, I'll be talking about answering this question, can DRAM do more than just store data? So before I get into the meat of the talk, let me quickly give you a background on my past. So I did my undergrad at IIT Madras. So there I got a Bachelor's of Technology in Computer Science. Back at IIT, I've been looking at problems specifically with respect to VLSI, CAD algorithms, placement routing, more algorithms than architecture, if you may say. And I started my Ph.D. at CMU in 2009. So I've been there for the past close to 7 years. So at CMU, I've been looking at problems with respect to computer architecture, mostly memory systems. I've done some work on DRAM architecture and virtual memory and caches. And in collaboration, I've also looked at problems with respect to compression and quality of service. Right. So in this particular talk, I'll be focusing my attention on my work related to DRAM architecture. Right. So let me quickly get into the problem. Right. So this particular slide shows the two components of a typical system. A processor connected to off-chip memory, which is predominantly built using DRAM today, and a channel connecting the two components. Right. And there are two trends going into future which are going to affect the system. So the first one is we're adding more and more compute to the processor side. We're adding more cores on the chip. We are putting a GPU on the processor and possibly more accelerators going into the same processor chip. On the other hand, because applications are accessing increasingly more data, we are adding more and more memory modules. So the compute power is increasing on one side, and the memory capacity is increasing on the other side. So to extract better performance from the system, the only bottleneck is the memory channel. Right? And the only way we know how to increase the bandwidth on the memory channel is just by increasing the frequency or adding more channels. Right? Both these approaches are very expensive and they are not very scalable, due to pin count limitations on the processor and also some electrical load limitations on the memory channel itself. So clearly, the story is not good for performance. We need to find out some way of extracting more bandwidth from the memory channel. But it turns out the story is not good in terms of energy as well. So this is actually a slide from Bill Daly's keynote talk at HighPeak 2015, where he talks about the amount of energy different operations in the system would consume. And I would like you to focus on two aspects. So on the leftmost here on the top, we have the energy consumed by a single 64-bit double precision operation. And it consumes around 20 picojoules. Right? On the other extreme, we have the energy consumed, but in transferring a single cache line from DRAM all the way into the processor, and it's around 16 nanojoules. So really, we are looking at a 1,000-fold increase in energy to move data from outside of a DRAM chip to the processor and actually performing computations on the processor. Right? So clearly, data movement is a bottleneck both for performance and energy. Right? So what is the community doing? Right? One recent research trend that has taken over is this idea called processing in memory. This is an idea that has been looked at in the past. There have been several works that have looked at this problem. But more recently, it's gaining more traction because of the bottlenecks introduced by the memory channel. And the idea behind processing in memory is to essentially put some small amount of processing logic closer to memory, which has much higher bandwidth to the memory modules, and then do some simple searching or filtering operations in the logic that is sitting there, and then send a much smaller amount of data over the memory channel to the main processor, which can do a much heavier computing. The question that this line of research asks is, what computation should we move to the processing in memory structure? Question.
So why can PIM have a higher bandwidth channel to the memory? Just because it's closer, is it the distance that matters, or is it something else?
So it really depends on the architecture. So let me give you an example. One architecture that is coming up these days is this 3D stacked memory architecture. So there's a technology called hybrid memory cube that is coming out of collaboration between Intel and Micron. If you look at that architecture, what it essentially has is a logic layer which is stacked with multiple layers of memory. And there, the connection between the logic layer and the DRAM stack is using this technology called through silicon vias, and not a traditional pin that is connected to the motherboard. So now you can have many more through silicon vias than pins, which increases bandwidth. Right? So it's essentially the architecture and not any other. Yeah.
Is there any breakdown of when you talk about the cost of getting memory, how much of that is what has to happen on the chips with all of the data being read out and then rewritten again, and maybe reading a lot wider set of data than you actually need, versus moving the data over that channel, versus signaling the address bits? And is there some of that you can't, getting closer is not going to help you with in terms of the energy that you need when you read the DRAM and have to write the data back in?
Extremely good point. So essentially you're saying, when I'm accessing data, there is a step where I have to take the data from the DRAM cells into some structure and then read the data out. So there are really these two components, and reading the data out on the memory channel, which component is consuming the most energy, and so I would say it's both of them are significant in some sense. And what I will be presenting in this work is essentially techniques which actually exploit the bandwidth closer to the DRAM cells, right? I'm hoping the rest of the talk will answer your question, but if it doesn't, we can really take it after that. But this is not what we are looking at in our work, right? So in our work, the question that we're asking is, today we use DRAM as just a storage device, right? So what we can do is write some value into DRAM and read the value at a later point in time. So if you notice, I have annotated the reads and writes with 64 bytes. It's essentially because commodity DRAM today is optimized to read and write wide cache lines, right? The question that we ask is, can DRAM do more? And the answer is yes. We have developed some techniques. We are hoping to increase the size of the font size of this yes as we identify more techniques, right? So what can we do? What can we do with DRAM? So we have it all started off with a technique where we actually showed that DRAM can be used to perform bulk copy operations. And more recently, we have developed techniques where we can use the DRAM architecture to accelerate strided gather-scatter access patterns. And our most recent technique is a mechanism to perform bitwise operations using DRAM technology. And in this talk, I'll be focusing my attention mostly on the two recent works, the gather-scatter DRAM, which is a mechanism to perform strided access patterns within DRAM, and BuddyRAM, which is a mechanism to perform bitwise operations completely inside DRAM. And finally, I'll end the talk with an overview of my other projects and future work. Okay. So let me jump into the first part of the talk. Okay. So in this slide, I'm essentially using an in-memory database table to describe what a strided access pattern in a modern system may look like. Right? So on the right, we have a picture of a database table with multiple records and multiple fields. I've highlighted the third field in yellow. Let's say that's the field of interest for a particular query. And depending on how the database is stored in main memory, that particular query can result in a strided access pattern. So if the database is stored as a row store where values of the same record are stored together, accessing the third field, which is the yellow blocks marked here, is going to result in a strided access pattern. Right? I'm not going to access values contiguously. Now, what is the problem with strided access patterns in existing systems? Like I mentioned, existing DRAM modules are optimized to access cache lines. Right? So I'm annotating the values with the cache line boundaries here. And what happens in existing system is whenever you access a particular value from within a cache line, the entire cache line is brought into the system. So if I access one of those yellow values, the system is actually going to bring in all the gray values as well through the memory channel into the processor caches. Right. And the result is going to increase the latency of completing the operation because I'm fetching more data than I actually need. It's going to waste the bandwidth, memory bandwidth, and also going to waste cache space. And like I mentioned, since the database actually consumes a lot of energy, this is also going to result in high energy. Right. The question that we ask is it possible for us to retrieve a cache line that contains only useful values? Right? Can I retrieve a cache line that contains only yellow values from existing systems without adding significant cost? Right? And the answer is yes. That's our proposal, the gather scatter DRAM, and we are going to specifically focus on power of 2 strided access patterns. Right? So just to understand the architecture that our system exploits, so this is a DRAM module. In most modern systems, a DRAM module contains multiple chips. I'm not sure if you're able to see those black boxes there, but those black boxes are individual DRAM chips. And in today's system, all the DRAM chips are connected within a module are connected to the same command and address bus, whereas each chip will have an independent data bus. So the result of this is whenever a read command is sent to the module, the command and the address are actually sent to all the DRAM chips, and each chip will independently respond with some piece of data. And the memory controller will put together all these values together to form a cache line. Right? In a typical system, the amount of data that a single DRAM chip would send out is around 8 bytes. So the size of the cache line would be 64 bytes. Right? And the memory controller will send the cache line to the processor. And like I mentioned before, the question we are asking is it possible for the memory controller to issue a read command with an address to the module, so the module actually responds with the yellow values? Right? And there are 2 challenges that we have to address towards achieving this mechanism. And the first challenge is what we call as chip conflicts, and this is very specific to power of 2 strides. Right? Like I mentioned before, the data of each cache line is spread across all the chips. So let's look at the first cache line. A simple scheme that the memory controller may use to split these values could be to map the first value to the first chip, the second 8 bytes to the second chip, and the last 8 bytes to the last chip. Unfortunately, because we have a power of 2 number of chips and looking at a power of 2 strided access pattern, if the second cache line is mapped in the exact same manner, the data is going to be mapped like this. And clearly, all the useful values are mapped to just 2 chips. Right? So in some sense, the memory controller has no hope of retrieving any useful value from, let's say, the first chip here. Right? So the bandwidth is essentially limited by the number of chips that have any useful value. The second problem is even if the values are somehow present in multiple chips, all the chips share the same address bus, which means the memory controller has no flexibility in specifying different addresses to different chips. Right? And one way to address this problem could be to have an individual address bus to each chip instead of sharing the address bus across all chips. But now that's going to increase the pin count on the processor, which is expensive. Right? So in this work, we are proposing 2 schemes which will address each one of those 2 challenges. Right? The first scheme is a simple shuffling mechanism which we call a cache line ID based shuffling. Right? The idea is fairly straightforward. We take the cache line and we pass it through a bunch of shuffling stages and then map the data to different chips. Right? So here, if you look at, there are 3 shuffling stages. The first stage essentially swaps adjacent values. The second stage essentially swaps adjacent pairs of values. And the third stage swaps adjacent quadruplets of values. But if you do this shuffling the same way for all the cache lines, it's not going to eliminate the problem. So somehow we have to control which stages are active for different cache lines. Right? So for this purpose, we use the cache line ID. We use some bits of the cache line ID to determine which stages are active. So in this particular case, the least significant bits are 1, 0, and 1. And stage 1 will be active, stage 2 will not be active, and stage 3 will be active. So essentially, we are looking, stage n will be active if the nth least significant bit of the cache line ID is set. So just to look at what this shuffling mechanism can achieve for us, This is the first 4 cache lines of the table before shuffling. And as you can see, there are a lot of chip conflicts. The useful values are mapped just to 2 chips. After employing the shuffling scheme that I described in the previous slide, that's how the data is going to look. And if you look at it, the cache line 0, because all the 3 least significant bits are zeros, it goes through no shuffling. The mapping between the cache line and the chips are exactly same as in the baseline. However, if you look at the other 3 cache lines, they've undergone some shuffling. And the result now is the yellow values are uniformly distributed across all the chips. Right? And you can actually show that for any, in this particular case, we are looking at a stride of 4. But you can show that for any power of 2 strided access pattern, we can use this scheme to uniformly distribute the data across all the chips.
You have to know the stride access pattern before you decide how you're going to do the shuffling.
That's a great question, right? So is the shuffling scheme dependent on what the strided access pattern is? It turns out the maximum stride that you can exploit is dependent on will be dependent on what shuffling you employ. So for example, with this scheme, you can actually do a stride of 8, 4, 2, and 1. And also a few other shuffling patterns, like I'll show in a few slides. But let's say you want to do a stride of 64 or 128, then you may have to use a few other bits of your address to do the shuffling. Right? That's a good question.
Which you probably need to know at the time. You write it, right?
Yep.
Oh, okay.
Yep. Yep. Question? Yeah.
So in pulling the data into the caches, what actually happens in the caches? Is it that there are empty slots in there? Because from the software view, right, it expects values to be contiguous. Mm-hmm. And right now, so what's actually happening in the caches?
That's a good question. Can you hold that question for a moment? I'll actually show you what the mechanism is going to do to the on-chip caches.
Yeah. Are there adversarial access patterns for which shuffling actually does not help or actually hurts compared to your before shuffling scenario?
So this particular mechanism would work for any power of 2 strided access pattern. But if you have let's say an odd stride, right? Now, so let's just take an odd stride. So now, an odd stride would actually not have the chip conflict problem at all, because if we typically have a power of 2 number of chips. So if you have an odd stride, because they are co-primes, all the values with the odd stride are actually going to be uniformly distributed across all the chips. So there, the problem will be the next component that I will describe. How you design the
how you design what to shuffle?
How you retrieve the data, right? Which I'll be showing in the next slide. Yeah.
Great question here. So clearly, this is how the data has to be layered in the memory beforehand, right? Anybody who's writing the data in the memory has to know that this is how it would be accessed, and therefore this is how the shuffling pattern should be, right? So what's the difference between that and, for your example, simply using a columnar layout of data? That would have also given you.
That's a great question. It'll be clear by the end of this section of the talk. But to quickly give you the answer, with a columnar layout, what you can achieve is you can achieve good throughput for a query that's going down a particular field. But let's say I have a system where I'm running both transactions and analytics, where the transactions want data in the row major order, and the analytics queries want the data in the column major order. A columnar layout is not going to give you the best performance. But what this mechanism is actually going to do is it allows you to access data both in the row major order and the column major order simultaneously. Right? So if you just look at this particular picture, as I'm showing here, the yellow values are mapped to different chips. Therefore, they can be retrieved using a single command. We still don't know how the memory controller is going to do it, but the memory controller can potentially retrieve them using a single command. But if you look at it in the row-wise, right? If you look at just the cache line 0, the cache line 0 is still mapped to different chips, which means the memory controller can still retrieve data in the row major order with a single command, and the column major order with a single command, right? So that's the benefit that this mechanism would provide, right? So to quickly jump into what the second part of the mechanism is, it's like I mentioned before, these values can now be retrieved using a single command, but the memory controller has to somehow provide different addresses to different chips, right? If you look at chip 0, it has to provide address 2, but if you look at chip 1, it has to provide an address 3, right? So how is the memory controller going to do it? Like I mentioned before, one way is to just have different address buses to each chip, but that's going to be costly. So what we actually show is the math behind this shuffling actually allows us to use a small piece of logic in front of each chip to locally compute the address at the chips. So which is why we introduced this notion of a pattern ID. Right. So the idea is to put a small piece of logic in front of the address bus that is connected to each chip, and that piece of logic is somehow going to compute which address the chip is going to access. Right. So similar to before, the memory controller is going to issue a read command with an address, but in addition to the address, it's going to provide a pattern ID. Now the pattern ID is going to somehow indicate what the strided access pattern the memory controller is expecting. Right. And what each chip is going to do is it's going to take the address and the pattern, and it's going to compute a new address to access, and then return the data corresponding to the new address. Right. So I'm zooming in on the column translation logic that is used by each chip. I don't want to get into the details here, but it's extremely simple. It just uses one bitwise XOR and one bitwise AND operation along with the chip ID to compute the new address. I'll quickly jump straight into what is the effect of putting these two components together. Right? Now there is only one layout of data in memory after the shuffling scheme, but so in this particular slide, I'm showing the first 32 values contiguously stored in DRAM starting from address 0. Right? If the memory controller issues a read with address 0 and pattern 0, it essentially gets a cache line that contains the first 8 values. Right? This is what happens in existing systems. Right? You get contiguous cache lines. So you access address 0, you get the first 8 values. You access address 1, you get the next 8 values. But if the memory controller uses read with address 0 and pattern 1, it actually retrieves a cache line that contains every other value. Right? This is without changing the layout in memory. Right? If it uses a pattern 3, it gets a stride of 4. This is exactly what our query wants. So instead of address 0, if you use address 3, you'll get every 4th value starting from this value, which is what the query in our example wanted. And if you use read with address 0 and pattern 7, it turns out you actually get a stride of 8. I'm missing a lot of patterns in between, and if you use those patterns, you actually extract values with different strides. Right. So that's the benefit of the mechanism. So just having a single layout in memory, just by changing the pattern ID, you can access different strided values from DRAM. Right. Now to answer Tunji's question on how this plays with the rest of the system stack. Right. So we have a DRAM substrate that can actually support different strided access patterns, but now we have to change the rest of the system stack to somehow exploit the DRAM substrate. So what I'm going to show in this slide is one way of exploiting it. There are many different ways that one can imagine. Right? So what we're actually going to do is, after the memory controller extracts a non-contiguous cache line from DRAM, it's actually going to store the data in a single physical cache line in the data store instead of splitting it across multiple physical cache lines. And there are reasons why we do that. Right? So to somehow identify these non-contiguous cache lines in the data store, what we show is we essentially have to append the tag store with the pattern ID. So essentially each tag entry in the cache will store with what pattern ID that particular cache line was fetched from DRAM. And we show that this is somehow a unique way of identifying each non-contiguous cache line. Right. And so this will also mean that when you have two cache lines, one that is having non-contiguous values and one that has contiguous values, now there can be an overlap, a partial overlap between two cache lines, and we that will require some support from the cache to maintain coherence. And we actually show in our paper that it's fairly straightforward to maintain coherence with the math behind the mechanism. Right. From the CPU side, we actually add two new instructions called pat load and pat store, which essentially is a way for the application to specify a strided access pattern to the processor. So, for example, if you use the pat load instruction, the pat load is similar to a load instruction. In addition to the register and the address, it also specifies the pattern ID with which the cache line has to be fetched. And the CPU checks the on-chip cache to see if this particular cache line with that pattern is present in the cache. If it is not present, the request is sent to the memory controller. The memory controller uses that pattern to actually fetch the data from DRAM and send the result back to the processor. Tunji.
So if I understand correctly, so if I have two threads, accessing the same piece of data using different pattern IDs, does that mean the data that I've fetched in will be duplicated in different cache lines?
Absolutely. So that's exactly what will happen. And as long as both threads are actually doing just reads, it's not going to result in any problem. Right. There'll be a problem only when there is a write, and we actually show that on a write, at each cache controller, we can locally invalidate the other overlapping cache lines as well. Now, there's a trade-off here, right? Let's say one thread is accessing values with pattern 0, the other thread is accessing values with pattern 3. I may be duplicating data in my cache, so I may not be using my caches very efficiently. That's some problem that we have not stressed in our applications, but the benefits of actually having data in the same physical cache line will outweigh the cost. Right?
Can I assume that all of the different data belonging to a pattern is always going to be on the same page?
Yes. Yes. If you're looking at, depends on what stride you're looking at. We didn't look at really large strides. In our examples, we looked at strides less than 64. So the data will be within the same operating system page.
Because, there are other CPU issues there relating to protection mechanisms.
Absolutely.
Pages are out, segments are still a mess if you worry about segments.
No, absolutely. Right. So, but in our examples, we did not encounter the problem. Right? But the moment we look at really large strides, to be frank, we don't. Our mechanism will not support super large strides, but it will also have problems that you are mentioning with respect to protection and.
Even the modest stride, if you're accessing something that's otherwise right at the end of the page, a single cache line might cross a page boundary, right? With a traditional one, it doesn't, because you only look at one. You specify a load of one word. And then whatever cache line that word is, because cache lines divide equally into pages that will sit in a page. But if I have a stride even of 2, then it could, and happen to pick the thing that's the last thing in the page, that'll cross, right? Or maybe
it's a good question, but because we are looking at power of 2 strides, and a system where a cache line is a power of 2.
So it's the same.
Yeah, a cache line is a power of 2. The operating system page size is a power of 2.
I get it.
So there. Yeah.
There's a crazy question. You can tell me that you don't want to answer it now or whatever. So you assumed upfront, with the stride pattern, that each value is stored in the memory only once. If it's replicated, it's replicated in your cache. You can take a completely different track. Like take your column and row example. I could have 2 regions of memory, because you said memory is plentiful, only the bandwidth matters. Store it row-wise, store it column-wise, and use your memory controller whenever there are updates to figure out how to somehow update both locations simultaneously. And when you're reading, read whichever pattern gives you the most cache efficiency. So why not?
I'll give you a one-sentence answer to the question. The on-chip cache has much lower data, right? So to actually maintain the consistency, right, using cache coherence protocol that I mentioned, there may be cases when you're writing to a value and the replicated version is not even there in the cache, right? But to keep 2 versions in memory consistent, we actually looked at that particular problem in a completely different setting. The write amplification actually kills performance, any performance that you can extract from the system. Let's take one last question on this and then move.
Yeah, you're saving energy by doing this. Are you also saving clocks, or how long does it take for it to return? Because these are coming from the different cache lines of the DRAM. Do you actually have to do individual cycles to get them together and then send it back, or does it take the same amount as a regular DRAM read?
That's a good question. So we actually save a lot on clocks, because when the memory controller issues a command, each chip does its operation simultaneously. So we get the strided contiguous cache line at almost the same latency as fetching any other cache line, right? So we're actually saving both energy and gaining performance. Okay? So let me quickly go into the evaluation and summarize some of the results. Right? We used a simulator to measure the performance. This is the GEM5 simulator that is widely used by the architecture community with a standard memory hierarchy. And for energy, we again used some tools that are used by architects to evaluate system energy. Right? And for workloads, we actually use the in-memory database workload that I mentioned. So there are 2 popular layouts for in-memory databases. One is a row store where, like I mentioned, the values of the same record are stored together. Then you have a column store where the values of the same column are stored together. And finally, we have the gather scatter DRAM, where we actually use an underlying row store layout, but we can actually fetch data both in the row major order and the column major order. I'm assuming that the table fits in with the power of 2 restriction that our mechanism has. And for the workloads, we have transactions which essentially update many values or read or update many values within one or few records. And we have analytics, which essentially looks at data within a field but across many, many rows. And more recently, there is this hybrid workload where both transactions and analytics are run on the same version of the database. Right? And it's well known that row stores are good for transactions, column stores are good for analytics, but neither one is good for both. I'm going to show you that gather-scatter DRAM can potentially obtain the best of both worlds. Right? So here is just a description of what the workloads are. We use a single database. We are just looking at the storage engine of the database. We are not looking at the concurrency control and all those aspects, just the throughput of the storage engine. So we use a single table with a million records. For the transaction, each transaction operates on a randomly chosen record with varying number of read-only and write-only and read-write fields. For analytics, we just use a simple arithmetic sum of all the values within a column. And the hybrid workload has 2 threads running on the same system. One is doing transactions, and the other one is performing an analytics query.
So have you mapped any real-world workloads to this type of workload? How will this match real workloads?
If you look at any traditional database engine, I mean, this is a problem that they are dealing with today through various other means. But we believe this approach can actually be better. We didn't run a real database engine on top of our mechanism because just setting it up and then running it would have taken me a much longer time. So this is just to demonstrate the benefits of our scheme, right? Okay, so on this slide, I'm showing the results for the transaction workload. On the left, we have throughput in terms of millions of transactions per second. And on the right, we have the energy consumed by different mechanisms for running 10,000 transactions. Right? And there are 3 mechanisms. And as it is clear, for transactions, the row store is significantly better than the column store. It's around a 3x improvement in terms of the throughput. And GSDRAM is able to achieve almost the same throughput as the row store, and the results for energy are almost similar, a 3x improvement in the energy compared to the column store. Right. On this slide, I show the results for the analytics query. On the left, we have the execution time, essentially the time it took for the system to complete the analytical query. And on the right, we have again the energy consumed by the query itself, end to end. And again, the story is very similar to the previous slide. The column store is much better than the row store here. And the GSDRAM is almost able to achieve the performance of the column store. It's a 2x reduction in execution time compared to the row store. And the story is very similar for energy. Question?
Curious, when you say end-to-end, is that energy in the memory system? Or just energy across the whole system?
Energy including the CPU, caches, the memory channel, and DRAM. Right. Having said that, I must tell you there are 2 components where we gain the energy benefits. One is we are actually transferring far fewer cache lines than the in this case the row store, right? And the second thing is we are actually reducing execution time, which means the amount of energy that they're going to consume in the process is also lower. Right?
Because you get okay. So, yeah. But can I mean, I don't know how accurate energy simulations are, but if that simulation is accurate, how does that play into my overall server power budget? Am I really looking at a 2x power reduction for?
You wouldn't. So the power is altogether different story, right? Because we actually don't change anything to reduce peak power or average power consumption. The power consumption will almost be the same, right? It's simply
higher, right? Because you've got a little bit of extra logic that's running on the.
You could actually argue that the power would slightly increase, right? Because we are actually we are stalling less on memory. So you could actually argue that
and you're stalling less.
Right?
So
The power consumption may actually increase.
Well, if you're through, okay, for a given workload, what are you telling me that my overall server energy budget will be halved? Sure.
If this is the only workload you're running on system, right? Which if you're doing this all the time, right? And having said that, I must also warn you, we are just looking at the storage engine here. There's a lot of other logic that is surrounding a database which we have not looked at. Right? So I'll.
You have more
algorithm is separate.
I know. I guess I really
just memory.
impressive.
You won't really save 2x of the energy in the entire system,
think
right?
so.
This isn't the Ethernet controller and the.
I guess what I'm saying is we don't even know how much this is a theoretical system.
Yeah. Okay. So this is the hybrid workload. Again, like I said, it's running 2 threads, one the transaction thread and the analytics thread. On the left, I'm showing the throughput for the transaction thread. On the right, I'm showing the execution time for the analytics thread. It turns out here, the row store is actually not performing as well as GSDRAM. In fact, GSDRAM outperforms both the row store and the column store. I'm not going to get into details of why this is happening. It's related to memory system interference. For analytics, the results are as expected. GSDRAM is able to perform as well as the column store and much better than the row store. Right? So really, the summary is with this mechanism for the database storage engine, we can potentially obtain the best of both row store and column store layouts. Right?
Although in that case, your coherence is actually going to have to shoot down cache lines, right?
Yes.
Which was not true in either of the other ones.
Yes.
Okay. And even with that, it still does.
Yeah.
Cool. Okay.
Yeah. So our simulator actually models the coherence.
Yeah, I assumed you did. Otherwise, it would be bogus. Yeah.
Sorry.
So yeah.
One more question on that. Are you simulating a multi-core, multi-socket system, or is it
It's a single socket, but multi-core system.
Okay, but you have a unified cache.
Yes, you have a unified cache. Yeah.
So
The last level
if you have a
cache
big
is
multi-socket server, and now you're going to see more coherence misses simply because these stride accesses are contending when they previously wouldn't contend. Have you thought about the impact that would have on scalability?
So now, we have thought about it. So here is the question that we have to ask, right? In the baseline system, we are spending more requests to DRAM to fetch the data, right? And in our system, we may potentially be invalidating, have more coherence misses. So now it's a question of which is more costly, right? Is a potential coherence miss costly, or is an off-chip DRAM access costly, right? The trade-off may be different for different systems. In this particular case, we found that the coherence misses are almost non-existent because my analytics thread is running on some piece of data. How likely is it that a transaction is going to update the exact piece of data that I'm operating on right now, right? So we actually didn't see many coherence misses in this particular case. Okay. So, just to summarize this part of the talk, there are many data structures. I use in-memory databases, but there are many data structures that exhibit multiple access patterns. And depending on how the data is laid out, only one of them will experience good spatial locality. Right? And we propose gather-scatter DRAM, where the memory controller actually gathers or scatters values with different strided access patterns. And we showed that it can achieve near ideal bandwidth and cache utilization for a power of 2 strides. And I showed an example of in-memory database where GSDRAM provided the best of both a row store layout and a column store layout. Okay. So this is actually a paper published in Micro 2015. So if you want, you can actually look at the paper for more details and more questions. Okay. Now, before I jump into the second part of the talk, how much more time do I have?
I think you're good. You should just dive in right now.
Okay. Okay. So for this part of the talk, we are going to dive into the details of how DRAM actually operates. Okay. So here is a DRAM module. Now, if we zoom into a DRAM chip, sufficiently far into the DRAM chip, right, because DRAM chip itself is a hierarchy of structures. So if you go to the lowest level, this is what each DRAM chip contains: a 2D array of DRAM cells connected to these components called sense amplifiers. Right, now, the DRAM cells themselves are extremely small, so we need some other component to actually extract the state of the DRAM cell. That's what the sense amplifier is going to do. Right, so now what I'm going to do in the next slide is essentially look at a single cell sense amplifier combination and see how that operates. Right? And then we will see how we can exploit that operation to perform more complex things using DRAM. Right, so this is that connection. So a DRAM cell contains 2 components. One is the capacitor, which stores the data, and an access transistor, which essentially determines whether this cell is currently being accessed or not. So the access transistor itself is controlled by the signal called the word line. And like I mentioned before, we have this sense amplifier component. I'll describe how the sense amplifier operates in a minute. The sense amplifier has an enable signal which determines if it's currently active or not. And the cell and the sense amplifier are both connected using this wire called the bit line. Okay. So in the initial state, both the word line and the sense amplifier are disabled. And both ends of the sense amplifier, the bit line and the other end, are maintained at this voltage level of half PDD, which is midway between the lowest and the highest voltage levels. and the capacitor we are going to assume it's fully charged. Right. So to access data from this capacitor, we're first going to raise the word line, which essentially is going to connect the capacitor to the bit line. Right. And now the capacitor is fully charged, which means it's at the voltage level of VDD. And just like water, which flows from higher levels to lower levels, charge will flow from higher voltage level to lower voltage level. So in this case, the charge is going to flow from the capacitor to the bit line, and it's going to increase the voltage level on the bit line slightly. Right. In this particular state, if we enable the sense amplifier, it is going to detect the deviation on the bit line. Essentially, it's going to compare the top and the bottom and say that, oh, the top is slightly higher than the bottom, and it's going to amplify the deviation until it reaches the extremes, right, where the top becomes VDD and the bottom becomes 0. And since the cell is still connected to the bit line, it's also going to replenish the charge on the cell. Right? So this is the system that modern DRAMs use to access data. Right? Now let's look at what happens with two cells connected to the same sense amplifier. Right? Now, let's say we want to copy data from the top cell to the bottom cell. Right? So initially we will activate the top cell, which we call the source, and it's going to go through the operation that I described in the previous slide, and the cell is going to get fully charged at the end of it, and the bit line is now at VDD. Now in this state, typically what DRAMs do today is to perform this operation called pre-charge, which will essentially take the bit line back to half VDD. But instead of doing that, we are going to activate the destination directly. What this does is it lowers the word line on the source, essentially locking the charge into the source cell, but connect the destination cell to the sense amplifier. But since the sense amplifier is already in a stable state, this cell is so small that it cannot switch the state of the sense amplifier. Instead, what's going to happen is the data on the sense amplifier is going to get written into the cell. So it's going to get fully charged. Right? So you can convince yourself that for any possible initial state, this is going to result in a data copy from the source to the destination. Right? And imagine this happening across an entire row of DRAM cells. That's what happens in today's system. Right? So we can actually do a multi-kilobyte wide copy operation using this simple scheme. Right? Now, let's look at 3 cells. So we started with 1, 2. Now let's look at 3 cells connected to the same sense amplifier. What we are going to do is we're going to connect all 3 cells simultaneously to the sense amplifier. Right? And here 2 cells are fully charged, 1 cell is fully empty. So the effective voltage level on the 3 cells is 2/3 VDD, right, which is still higher than half VDD, which is the voltage level on the bit line. Right? So when we do this connection, at the end of the charge sharing phase, where the charge flows from the cells to the bit line, there's still going to be a positive deviation on the bit line. And if you enable the sense amplifier in that state, it's going to actually push the bit line to VDD and also all the 3 cells to the fully charged state. Right. Now if you look at this particular operation, let's say the final state of the bit line as output, and let's use A, B, and C to denote the initial states of the 3 cells. We can write the final state as AB plus BC plus CA. This is essentially the majority function. Right? If at least 2 cells are fully charged, my final state will be 1. Otherwise, my final state will be 0. It turns out using Boolean algebra, we can actually rewrite this expression as C times A or B plus not C times A and B. What this expression tells us is if I can control the initial value of cell C, then we can actually use this majority operation to perform a bitwise AND or a bitwise OR of the remaining 2 cells. Right? Again, imagine this operation happening across an entire row of DRAM cells. Right? So essentially, we have a mechanism to perform a multi-kilobyte wide bitwise AND or bitwise OR operation. Right? Now, to quickly complete the picture, let's look at how we can perform negation using the sense amplifier. Right? Like I told you before, the sense amplifier has 2 parts. In the stable state, the bottom part is always the negation of the top part. Right? So if we had a mechanism to somehow connect a cell both to the top and the bottom, that will be great. Right? Which is where we use this notion of a dual contact cell. A dual contact cell is essentially a 2 transistor, 1 capacitor cell. Right? It's used in many other schemes as well. So one transistor connects the cell to the bit line, the other transistor connects the cell to the other side of the sense amplifier. Right? And we call the word line that controls the transistor that connects the cell to the bit line as the regular word line, and the other word line as the negation word line. Now let's look at how we can take a source cell and store the negation of the source cell into the dual contact cell. Right? So initially we will activate the source cell, which will go through the series of steps that I described in a couple of slides before. And at the end of the whole operation, the source cell will be fully charged. The bit line will be at VDD, but the other side of sense amplifier will be at 0, which represents the negation of the data that was there in the source cell. Right? In this state, we activate the negation word line, which essentially connects the dual contact cell to the bit line bar or the other side of the sense amplifier, and this essentially drains out all the charge that is there in the dual contact cell. So essentially, we have the negation stored in the dual contact cell. So really, what we have is we have this 2D array of DRAM cells, and we can actually perform copy operations between rows. We can do bitwise AND and bitwise OR, and we can do NOT. Right? So if you put all these operations together, we essentially have a scheme where we can do any bitwise logical operation at a row granularity within the DRAM chips.
Very quick question. So the first three operations, you don't need any changes to the architecture of the DRAM cells, but for NOT, you do need some process change, right? Is it some transistor that's already present at the sense amp that you can reuse?
That's a great question. So what we actually show is the dual contact cell, they need two transistors, right? So what we can actually do is we can just not use one row of capacitors to store data. Instead, use those transistors to actually, for the repurpose one row of transistors to act as negation transistors for the dual contact cell. Right? That's a good question. But you are right. I mean, for the first three mechanisms, we actually only need changes to a component called the row decoder that is sitting in the periphery of the DRAM array. Okay, so just to look at how this scheme can perform, in this slide I'm going to compare the throughput of our mechanism with what you can achieve using existing systems. So essentially what we are doing is we are taking an Intel system and we are running a micro benchmark that is performing a bitwise AND of two vectors A and B and storing the result in a third bit vector C. Right? And we are repeating this operation and figuring out what is the throughput that we can achieve for this particular operation. On the x-axis here, we are increasing the size of this bit vector, right? Starting from 32 kilobytes all the way up to 32 megabytes. Right? So the working set of the application is somehow 3 times this size, right? Because we are having three such vectors. And the y-axis is showing the throughput of performing bitwise AND or OR for this particular benchmark in terms of the gigabytes of result produced per second. Right? So this is the throughput that you can achieve with one core. Right? Before dissecting this result, let's look at what happens if you have 2 cores. Right? With 2 cores, I'm getting much higher throughput on the left-hand side. With 4 cores, I'm getting even higher throughput. Right? So this step function is the result of multiple levels of on-chip caches that you have. Right? So essentially, if you look at the 4-core, this is when the entire working set fits into the L1 cache of all the 4 cores. So this is when it fits into the L2 cache, and this is when it fits into the L3 cache. Right? The key here is the moment the working set stops fitting in any level of the on-chip cache, the throughput that you can achieve with any number of cores is almost the same. Right? It doesn't matter whether you have 1, 2, or 4 cores. You have to go to memory, which means you are memory bandwidth bound. Right? With Buddy RAM, we can actually achieve close to 10 times the throughput of just going to memory. Right? And this is just using a single bank, right? Whatever mechanism I showed. DRAMs typically have multiple banks that can be accessed simultaneously. If we employed more banks to perform the Buddy RAM operations, we can actually get even higher throughput. Right? Right. So in the previous slide, I showed the results for bitwise AND and OR. So here I'm just summarizing the results for all bitwise operations. On the left, I have the same throughput result, but for different bitwise operations. I'm comparing the throughput of Buddy RAM with the throughput you can achieve when the working set does not fit in any level of the on-chip cache. Right? As you can see, for NOT, you get the highest throughput benefit. When you have more complex operations like XOR and XNOR, the improvement is not as much, but it's still close to 4x the throughput that you can achieve with existing systems. Right? And this is again using just one bank. Right? And the bigger story is we can achieve significant reductions in energy because we are avoiding all the memory transfers on the data channel. So we essentially is a very, very efficient mechanism to perform bitwise operations. Right? And we looked at some applications for this particular DRAM substrate. Right? One is we can simply use this to implement set operations. Right? So if we can represent a set using bit vectors, and if the operations mostly involved insert, lookup, union, intersection, and difference, then we can actually show that this approach may be much better than using a traditional red-black tree style implementation for sets. Right? And we actually looked at a real-world case where this may be useful is this notion called an in-memory bitmap indices. Right? So this is you can think of it as a replacement for the B-tree based indices that is popularly used by databases. So if I'm a website and I'm tracking millions of users, then instead of having B-trees and other kind of indices to track different attributes, I'll just use a bit vector to denote different attributes of the user. For example, is the user a male, right? I can use a bit vector to represent that. Is the user under 18 years of age? I can use another bit vector to represent that. Did the user log in on this particular day into the system? Did the user upload a photo into my web page? So you can use bit vectors to track all these pieces of information, and you can have interesting queries on the database, which will essentially involve performing bitwise operations on these different bit vectors. And we actually show that Buddy can improve the query performance for some of these queries by close to 6x, right? All right, so
doing the end-to-end query performance, because I see how you can, right, so you have a great big bit vector, you do an add, but the query then is going to say, find me all the set bits, which is going to end up sucking the cache lines into memory anyway, right?
So that's a great point, right? If we don't have a mechanism to do bitcon, so what if my query involved bitcon? So in fact, the query that we looked at, so again, it really depends on how often are you performing these reduction operations as opposed to bitwise operations. So in fact, the query that we looked at is doing a bunch of, so let's take a query where I'm looking at how many users how many male users under the age of 18 logged into my website in the past 1 week and uploaded a photo. You're going to perform a bunch of bitwise operations, right? On many bit vectors, and then send the result into the processor, right? So the amount of data that you're transmitting is actually much lower than what you do in the baseline. Okay, it's a great point. So just to summarize, DRAM can be more than just a storage device. We have looked at, I presented 3 different techniques to perform different operations inside DRAM. And the bottom line is we aim to achieve high performance at low cost. So essentially getting order of magnitude improvement in performance for the respective operations while incurring very few changes inside the DRAM chips. Right. I have time? Okay. So if there are any questions?
Keep going.
Okay. All right. So in the last part of the talk, I'll just present a quick overview, or it's essentially a list of other work that I've done at CMU, and go over some of the future directions that I'm planning to look at. Right. So these are the works that are part of my PhD thesis. I essentially presented the first 3 mechanisms. I think I should have probably changed this ISCA as submission. We got the results back. It didn't get in. These are the other 2 components of my PhD thesis. One is called page overlays, which I presented ISCA last year. The idea here is existing virtual memory frameworks, which are page granularity. We show that they are inefficient to perform certain fine-grained memory operations. Right? If you take copy on write essentially happens at a page granularity. So even if I modify a single byte within a page, it's going to result in a full-blown page copy. Right? So essentially, this particular framework is looking at can we make such operations more efficient, because the hardware can inherently track cache lines. Right? So the processor can track which cache lines are present where. So can we use that capability to enable a more efficient framework? Right? That's what this particular idea is looking at. So the dirty block index is attacking another problem, which is essentially present in the mechanisms that I presented. So let's say we are performing an in-memory operation. Right? Let's say I'm performing a bitwise operation on 2 source values and then storing the result in a 3rd row in DRAM. What if the cache, on-chip cache, has some dirty blocks from those source pages? Right? Now, before performing the bitwise operation, we have to actually flush the data of the source rows from the on-chip caches into DRAM before we can actually perform the operation. So essentially, the flushing is on the critical path of performing the bitwise operation in memory. What the dirty block index is going to allow us to do is to accelerate this flushing mechanism. So essentially, it's a scheme where we can identify dirty blocks of a particular DRAM row very efficiently and also flush them to DRAM very efficiently. Right? In the past, I've looked at, this is early years of my PhD, I've looked at some mechanisms to improve on-chip cache utilization. So these are essentially algorithms to control cache insertion and algorithms to manage prefetch blocks in on-chip caches. And I also done a bunch of works in collaboration with other PhD students looking at practical data compression for modern memory systems. So this is essentially in collaboration with Gennady Pekimenko, who I believe interviewed here a few weeks ago, and also looked at problems with respect to slowdown estimation and integration. So essentially, when multiple applications are running on the same system, applications will get slowed down because there is interference at shared resources. Now, it turns out that when the slowdown is actually dependent on which applications you're running with. So there is not just slowdown, but there is also some kind of unpredictability in the slowdowns depending on which applications you're running with. So can we actually enable hardware support to allow the operating system to understand what your slowdown is going to look like? So those are mechanisms that we looked at in collaboration with Lavanya, who's currently at Intel. And I've looked at some other low latency DRAM architectures with other students, primarily Yoongu Kim and Donghyuk. So Donghyuk was a researcher at Samsung for several years, and it's from him we gained all the DRAM knowledge in the group. Okay. So for future directions, there are for the near future. I mean, there are definitely some works that have come out of my thesis that I'd like to look at, essentially extending our mechanisms to the full system. But these are directions that are resulting from some imminent trends in architecture. Right? So the first one is new memory technology. So essentially, there is a bunch of different technologies that are mostly in research now, but that are also going to be imminent. These technologies have two characteristics. One, they are non-volatile. So essentially, data is persistent, unlike in DRAM, and they have some challenges with respect to the read-write characteristics that they have, both in terms of performance and energy. So essentially, this is a non-volatile memory technology that can be accessed using load-store primitives, right? But today, if you look at any level of persistent storage in the system, they are mostly block access, right? SSDs or hard drives. So how will these technologies affect the way we think about applications, right? If you have a database, do I have to still write logs, or how does it change in existing systems, right? The second direction is heterogeneity. Right? We already have a lot of heterogeneity in the system. Like I mentioned before, we have CPUs, we have GPUs in the same system. Intel is probably going to put an FPGA on chip, right? And we are describing all these processing and memory mechanisms, buddy RAM, gather scatter DRAM. If a system has all these different computing resources, how does the operating system determine where to schedule a particular task, right? And the heterogeneity is also seeping into memory, right? So today, memory is mostly monolithic. We have one kind of DRAM sitting in the system, but in the future, you can expect fast, low latency DRAMs, high bandwidth DRAM, low power DRAM, all put in the same system, right? With this amount of heterogeneity, how does the programmer specify what the application should do, right? Because unlike heterogeneity in a NUMA system or a multi-socket system where the architecture is still homogeneous, here we may have different compute units which require different pieces of code to run. So how does the application specify, or the programmer specify what the application should be doing, and how the compiler should compile a single piece of code to different architectures, and how does the operating system schedule different applications on these different architectures? I think there are many interesting questions to be answered in this particular space. Right? And finally, something that has picked up in many places, including at Microsoft, essentially application-specific system design. That if I know my application, and if I know this is the most important workload that is going to be running on a large system, can I actually go and think about the system end to end and modify both hardware and software to essentially extract the maximum efficiency out of the system, right? I mean, Microsoft Research here is doing that has done that for Bing Search already, the Catapult system, and now they are looking at expanding this to other areas. So again, I would like to look at problems in this space and look at how I can use my architecture knowledge to contribute to ideas here. Right? So that's it. Thank you for running my talk. And question.
So have you had time to talk to hardware vendors, and you can comment on what's their reaction to GS DRAM? Particular, how expensive do they think this would be for them, or be easy for them to actually add this new logic to their module? Like, what's their sense?
That's a good question.
What's the reaction of industry to this idea?
So I'll give you a two-part answer. So one, we have been in touch with throughout the research. We have been in touch with some DRAM manufacturers,
okay,
and like designers of DRAM, like DRAM research teams, and here is what we hear from them. From a feasibility perspective, there is no challenges here. So all the mechanisms that I described are feasible to implement in DRAM. But they're going to increase cost. They're going to increase cost because there are some yield implications to our mechanism. Let's say we have buddy RAM, right? Which means we have one more feature in my DRAM, which also means that there may be many more modules that can fail because they don't support this feature, right? So really the question here is there, what is the killer application? That's the question that they ask us. And we go and tell them, hey, in-memory database bitmap indices. But that's not sufficient for them. Right? They want some bigger vendor like say Microsoft or Google to actually tell them, hey, we really care about this, right? Which is where I think research which will show there are some really important applications that can benefit significantly from these DIMMs can that will push the DRAM manufacturers to actually go and even implement some of these things. Having said that, there was a keynote talk at Micro this year where I was presenting the gather scatter DRAM work. This was from Thomas Pawlowski from Micron. So he was giving a keynote on where he thinks new memory technologies are going, and there he mentioned look at ideas like gather scatter DRAM. So it was I think from that perspective we really think these are easily implementable mechanisms in DRAM. We really need the killer applications to actually push the manufacturers to do it.
So that Intel is going to ship him? Is that, or did you?
No, I did not. So I was
going to ask you where I can buy it, but
I'm saying I was saying Intel is probably going to put FPGAs on chip.
Okay.
You may not get a chip today, but maybe in the near future.
So if that happens, then that's sort of a more general mechanism, right? So then you don't need the kind of
FPGA on chip.
Yeah.
So I think this actually goes back to his point, right? His question initially, where at the end of the day, right, the real bottleneck is actually taking the data from the DRAM cells and pushing it over the channel. Now you can increase the bandwidth on the channel and put an FPGA or whatever piece of logic that you want. That is going to be good for some operations. So definitely, the mechanisms that I have described here have limitations in the sense you cannot do every single computation using the mechanisms that we have described, right? But at the end of the day, any system that separates memory and computation and has a channel in between will eventually become bandwidth bottleneck because we always want more computation and more data, right?
It's unwrapped. Right, there are plenty of apps that would things get stuck on the disks, things get stuck in the network. Some will be.
Yeah.
You made too strong a statement.
Mm-hmm. So
you said any application will. And that's
okay. I think I was being too strong. Yeah. Point taken.
I'm just quibbling.
Yeah. Point taken.
Yeah. So in the first part of your work, you suggested you will augment the diagrams. Typically, cache accesses are on the critical path of a processor's frequency. So does your technique impact clock frequency? Did you analyze that aspect?
So just to repeat this question, so we are adding this pattern ID to the on-chip tag stores. Will that have any effect on the cache access latency? So essentially what our mechanism does is it adds a few additional bits to the tag itself. So if your tag was 32 bits, with 3 additional bits of pattern ID, it will become 35 bits, right? So now, we did some simulations using cacti, which is essentially a cache area and latency estimation tool, and we did not find it increasing the latency.
So is it as simple as that? I thought that because you're accessing words from different areas and putting them in the same cache line, mm-hmm. you would probably need a way to sort of have indirections saying, okay, this data, although this is not supposedly in this cache line, but actually is. Or is it just as simple as?
Again, there are many ways of exploiting our work, but the way we looked at the application actually specifies the pattern ID also. So let's say the application accessed a cache line that contained contiguous values, right? And then the application actually wants to access a cache line which has strided values starting at the same address. Right? Now let's say it's accessing the first value. Now even though it is already present in the on-chip cache, it will actually result in a cache miss because the application is looking for a different pattern, and it will go all the way to the memory controller, and the values will be fetched from DRAM. Right? So it's not looking at values at an individual granularity. The application is the on-chip cache is still storing things at the cache line granularity.
You still need that for There's a right, you need it for coherence.
Yes, you need it for coherence, which is where the question is, when I'm writing to a particular cache line, what are all the other possible cache lines that can potentially overlap with this cache line that I have to invalidate, right? So I did not go into the details in the talk, but we have a very simple mechanism wherein the cache controller can actually list which cache lines can have to be invalidated, and it will invalidate those additional cache lines as well. So in terms of messages going between cores, it's still a single message that is going, shoot down this particular cache line, except the cache controller is locally doing some additional invalidations before it sends an ACK back to the original code that sent the invalidate. So that's where I think there's a trade-off between how often are you doing these additional invalidations as opposed to how often are you fetching additional cache lines from the DRAM. I think there'll be a trade-off there. Question?
In the second part of the work, it appeared that you would be activating multiple rows in the DRAM to perform your logical bitwise operations. Now, is that a standard technique, or did you have to do spice simulations to figure out whether it will actually work, because all of that is analog circuit?
Yeah. So we did some spice simulations. I mean, and what I can tell you is in simulation it works, right? But when you go to real DRAM, there are other considerations, right, which is completely outside the scope of an academic institution to do those studies. But having said that, like I mentioned, we have been in touch with some DRAM manufacturers, so they expect the schemes to work.
But they are afraid about the yields, which means that they are expecting some impact of these techniques.
No, definitely. So if you look at the existing DRAM market, right, it is the DRAM design itself. I mean, from whatever I described to you, you probably already know 50 to 75% of how DRAM works, right? So the DRAM design itself is very, very simple, but the real cost, or where DRAM manufacturers have an edge over any other place that can actually manufacture a DRAM, is how the techniques that they use to optimize DRAM for yield, right? And those are not public at all. So we don't know all the techniques that they employ to maximize yield. So which is why I'm commenting this is a new feature and it may affect yield, which will be a big concern for them. But if Microsoft says, okay, today I'm paying $10 per gigabyte, but I'll be willing to pay you $100 per gigabyte for a system that will also allow me to do bitwise operations, maybe they will consider it. Maybe, right?
Thank you.